This video takes a look at the traceroute command that's in the newer Linuxes. This is Backtrack 5 Release 2, and the version of traceroute inside of here is version 2018. So this is one of the newer releases, and the new traceroute has more features than the older traceroute. Specifically, you can use different kinds of packets to do the trace routing, which is a relatively recent upgrade to the traceroute. The Windows traceroute or traceRT command still uses the ICMP echo request, and it's the only type of trace routing that it can do, which severely limits its usefulness. Firewalls and other host devices often block ICMP traffic, especially if the ICMP traffic is crossing over a router. So if you tried to do ICMP against even most home networks, that traffic is going to be blocked, much less the corporate type networks. So being able to use traceroute with different kinds of packets is useful. So this version of traceroute can do several different kinds. It can do a TCP, a UDP, an ICMP trace routes, and then it has a default UDP trace route. We'll take a look at these. So the flag for ICMP is the -- ICMP, or just capital I. TCP can be also -T. By default, it does a UDP, and there's also a variant on the UDP type of trace routing that can be activated with the --UDP or --U. And there is a slight difference between the default trace route with UDP and using the UDP for switch for trace routing. So one of the things we can do to help keep track is we can go ahead and set up a listener, TCP dump, to listen to the network traffic. So we're going to be looking at the machines on the virtual network, which are in the 56 subnet, and we need to figure out which of these devices is listening to that subnet so that we can capture the traffic for that subnet. So ETH1 is bound to the 56 subnet, and ETH2 goes off to some other private network, so we want to ignore ETH2 and use ETH1. So I'll do TCP dump -I for interface, ETH1, -X, capital X, to show the packets in ASCII and hex, -VVV verbose, -NN to keep from using host names or port names and instead use host IPs and port numbers, -S0 to get the entire packet, and we're going to write these packets out to a file which we'll call packets. And we'll go ahead and put that in the root directory so we can find it later. And then finally, there's going to be a lot of noise on this VirtualBox network. We're going to try to restrict what we capture with a host filter. And we're going to filter for this particular host. So host filter captures packets going either from this host or destined to this host. And so it's equivalent to saying source of 101 or dest of 101, but you can do it on one filter. This TCP dump is listening on ETH0, and so far it's got 0 packets, and that number will go up as more packets come in. We're capturing 65,535 bytes because of the S0, and we're capturing on ETH1 because of the -I ETH1. So if we go back over to the traceroute area, let's go ahead and do a traceroute on the Windows box at 192.168.56.102. We're using the default. We didn't use any switches at all. And that comes back with an answer. And we got 8 packets. Now we'll do a trace route with the -T option, which is the TCP, and we got an answer. We'll do the -I, which is ICMP, and then we can do the -U, which is the modified UDP. And all of those trace routes were successfully able to complete. So now let's try the machine at 103. So we can do them in the same order. We'll do the default, and it timed out. Do -T, and it worked. We'll do -I for ICMP, and it worked. And we'll do -U for UDP, and it should time out. Okay, looks like it did. So what's the difference? Machine 102, we were able to trace route using all 4 types of packets. The UDP, that's unmodified from port 33434, the trace route from TCP, which defaults to port 80, the trace route from ICMP packets, and the modified trace route UDP, which goes to port 53, that's DNS by default. But then when we hit Windows box at 103, both of the UDP style trace routes timed out while the TCP and the ICMP still worked. So what's the difference in this behavior? Well, it would help to know what the targets are a little more carefully. So we're going to do an nmap-o for operating system type. And then we're also going to restrict the nmap to looking at just those 2 boxes. So that's 102 through 103. And we'll try to get an idea of exactly which Windows operating systems are running on the 2 boxes. So again, we want to keep in mind that 102, all of the different trace routes worked fine, but on 103, all the UDP style trace routes failed while the TCP and ICMP trace routes worked fine. So this is box 102, and box 102 is a Windows XP, or it could possibly be a Windows 2000. Nmap has narrowed it down to either a Windows 2000 or a Windows XP SP0 box through SP1. Well, certainly an older box. Then we have the box at 103, and that has been declared by Nmap as being a Windows XP SP3, so much later version of XP. And in particular, the version of XP at the 103 IP address is at least Service Pack 2, obviously it's Service Pack 3, while the box at 102 was not at least Service Pack 2. And this explains why the different TCP options with this new TCP dump tool gave different results. The older Windows boxes didn't have the current version of the firewall in them, whereas the ones after SP2 did. Additionally, the firewall in Windows XP SP3 blocked UDP traffic for the most part by default, and which explains why the UDP packets from our trace route were blocked, but then the TCP ones made it through. Now, the TCP one did get a little bit lucky. There happens to be an exception on this particular Windows XP SP3 box for port 80, and the trace route in Linux that uses the -T or --TCP flag does happen to hit port 80. But what if we wanted to try to trace route on another open port? We can do that because Nmap tells us that 139 is open, so we don't have to go at it blindly. We could have done an Nmap scan and then use that information to feed back into traceroute. Now, of course, a lot of this is just for academic purposes to help our understanding, because Nmap has a traceroute built into it, which would have worked just fine. But going through these exercises helps to understand what's going on with the boxes and why the different traceroute options are working the way they are. So the traceroute port can be passed in. So we could have done a dash. We'll do it a little bit different this time. Instead of saying -T, we can say --TCP and do a port 139. and we'll give it a try, and it worked fine as well. But if we were to try port 138, let's say, which according to the Nmap scan doesn't appear to be open, we may get a different result. And we're going to have to wait a second because it's probably going to time out, obviously. So this helps us understand, because we're able to reproduce results at will, that the reason that the TCP traceroute worked is because it happens to default to port 80, and the box 103 happened to have that port with a firewall exception open because the owner of the box is serving web content. And we can confirm that it is serving web content with Nmap service option. So if we do a SV against the target, again, this is a little academic because we could have passed all this in on the initial Nmap scan and it would have given all this away, but we're doing it a little bit at a time as we work through why the boxes are acting the way they are. The SVI option is a service version scan, and it basically sends probes against the open ports, and it tries to match the response against a large list of possible responses. And if it sees a match that matches a particular response, in other words, the server talked a certain way, it can tell what kind of server it is, sometimes with a lot of detail. For example, in this case, it was able to get the actual version number of the Apache server. And in some cases, it may just come back and say it's Apache, but in a lot of cases, it is able to actually tell right down to the versions, or at least give you a partial version. So it does indeed look like there's a web server running, and that explains why port 80 was made an exception by the owner of the box. So what about the TCP -I option? Why did that work on box 103 when the UDP versions were blocked? Well, and the reason is most likely right here. Nmap says that this Windows XP box has port 445 closed. However, there's something listening on it. See, if the box had been blocking that entirely through, let's say that it was firewalled off by some kind of firewall or some kind of host system or whatever, what we really should have got back was a filtered, meaning that either there was a timeout or the firewall just dropped the packet or whatever. But in this case, we actually got a reset back from the box. That's what Nmap uses to display a closed, is if it sends a SYN and receives a reset acknowledgement back, it'll say closed instead of filtered. So it's likely that the box is got something going on 445, some kind of Samba server, and we may have been able to use that information to figure out that the ICMP is probably allowed through the firewall, because on Windows XP SP3, when the 445 port is in use, even if it's blocked to certain machines, it automatically enables the ICMP echo requests in the firewall. Also, the owner of the box can go into the advanced firewall settings on the ICMP area of the advanced tab, and they can manually check off and allow ICMP echo requests as well, which is just as good of an explanation. It's going to be hard to tell exactly what the reason is, but the fact that it's SP3 with 445 port being having a reset packet sent back from it may indicate that that's why that the ICMP version is working. And then this tells us more or less why all the TCP options, or all the traceroute options, worked on box 102. Since it's prior to Windows SP3, the firewall really didn't block anything in those versions. There really wasn't much of a firewall that was added in Service Pack 2, where it had a more modern firewall that we think of today as having the ability to make stateful decisions about packets. So let's take another look at the traceroute on box 102 against the 445, just to see what will happen. And it actually did work. So even though the port is closed, the firewall isn't really blocking the traffic to 445, and so the trace route was actually able to get a good trace route on the box, and that's a pretty interesting result. So this new trace route in the relatively newer versions of Linux has the ability to do what they call layer 4 trace routing, as made popular by the LFT or layer 4 traceroute tool, which is still available today and actually has more features than this traceroute. But this native traceroute inside of Linux has made some really nice improvements in the last couple of years and has a lot more capability in it now, with the ability to specify either UDP or TCP or ICMP packets, and also declare the port that's used in the TCP packets and the UDP packets. That's a huge advancement. So we've gathered really too many packets almost to make practical as we've done these different trace routes, and we're just going to take a quick look at a couple of those to help understand how the trace route is working inside of Linux. Now you can go to the man page and read about the trace route, and it'll tell you all about how it works, and certainly read that before even attempting to do any of this. But it is interesting to go back and look at the packets captured and just piece back together what's going on. So while TCP Dump is an excellent tool for capturing the packets, I find it a little bit easier to read the packets in Wireshark, just because you have the graphical view and then you can do some of the drill down features using the GUI. So our file is called packets again, .pcat, and we're just going to run this as a background job in case we want our command prompt back. So this is one of the first scans. We can see the ARP where our box 101 was asking around to see if anybody knew who box 102 was, and someone responded back that they knew that box 102 was this MAC address here through the address resolution protocol. And so the box that replied back should have been the VirtualBox controller. So there's the ARP. And then there's 3 UDP packets in a row going to destination port. This is going against box 102, destination port 3347, 8, and 9 in a row. And it's pretty well documented that that's how the traceroute command in Linux works, and the default mode is it fires off UDP packets at 443 and then 434, and then moves its way up from there. And then it just keeps adding on 1 digit each time. So you can kind of see that you'll get these ports where it's sequential. So that's the default behavior. And then our Windows box 102 was really kind. It actually returned ICMP packets back to us, saying that basically it's unreachable. So if we drill down on this packet, we should see that it's type 3 unreachable. So it's type 3 code 3, which just means the Windows box is being friendly, and it's saying that you've obviously made a mistake because you can't get to this port. The reason that's friendly is because if the Windows box had just ignored us, we would have had to have waited for a timeout to occur. So we would have chewed up a lot more time sitting around waiting to figure out that we weren't going to get anything back than the box just telling us that up front. And so we get the same destination unreachable back for each of the 3 packets. Then we had tried the -T option next. That was the TCP. And like we said earlier, this traceroute packet went to port 80. And that's the default, but we had used the -P later in the video. We had used that to set it to port 139 because we saw Nmap told us that 139 was open, and then we had contrived an example where we sent it to 138 because we knew that Nmap said that port was filtered, and we wanted to make sure and find and really notice that traceroute was going to fail against a closed port after we noticed that it had worked against an open port. And then finally we concluded by hitting 445, a closed port, but noticing that the traceroute worked anyway. So this TCP packet here was the first one that we sent, and then it was followed up by a second one, and then followed up again by a third one. And the traceroute tool tends to do this, repeat this pattern where it sends 3 packets back to back to back in an attempt to try to fingerprint the machine. Now eventually 102 sent back a packet back to us over TCP, and we can see right here that there's that reset acknowledgement. Now that's important because that helps explain why the traceroute against 445 worked, even though we clearly saw that Nmap said the port was closed. So closed from Nmap's point of view means that a reset acknowledgement had come back. So instead of marking it as filtered, it marked it as closed, which means that Nmap knew a little bit more about the port than just a plain old filtered, because a filtered could be that no response came back at all and it just a timeout occurred. So in that case, it's most likely filtered, but it could have been a little bit ambiguous if it just been a plain timeout. But a reset ACK is actually nice to get back because it's a positive acknowledgement. Now, it's not an acknowledgement that the port's open, but it is positive acknowledgement from the point of view that gives us the information that we were looking for. Is the port open or closed? It's closed. We can move on and don't waste a lot of time waiting around for timeouts to occur. So since the reset ACK actually worked for port 80, then we would know later on that it would have worked for 445 as well when we did the later experiment. So we have some more TCPs going out and so on and so forth. And then eventually we did the -I option, and that used the ICMP packet. And sure enough, we can see those here. So it's a type 8 echo request, and these packets are sent out in hopes that the machine will send back an echo reply in response to the echo request. And then here we can see that 102 responded with an ICMP echo reply, and we can go down and see that's a type 0 code 0. So a type 8 code 8 is the request. So here's type 8 code 0, excuse me, not code 8. And then the reply is 00, type 0 code 0. And of course, traceroute sent a whole bunch of those in trying to map the network. So now the time to lives on traceroute packets are the ones that are really interesting. We can see that traceroute sent a time to live of 1, then 2, and then 3. Of course, it sent 3 1s in a row, and then 3 2s in a row, and then 3 3s in a row, because that's the behavior is it triples up the packets that it's sending to increase the chances of getting a good response. So time to live of 4 and so on. So it was trying to measure the amount of time that was decremented off the time to live. Really, it's not time, it's hops. So it was trying to measure the number of hops that were decremented off the time to live as they were coming back. And let's see if we can find our last packets. They should be some UDP packets. Now, Nmap says they're DNS packets, but we have to recall that they are they're UDP going to port 53, which of course is a type of, generally a DNS. So a DNS can run on TCP 53 as well, but commonly it runs on UDP 53 for smaller queries, and if the query exceeds a certain size, then it'll switch over to TCP. But by default, UDP 53 is DNS, and Wireshark is saying, well, I think this is the DNS protocol. Naturally, we know it was actually traceroute, only because we sent the packet. So there is the malformed DNS packet picked up, and we know it wasn't really malformed on purpose. It was just the fact that it was trying to hit that port, and it wasn't a real request for DNS. So by looking through the different captures that we captured from TCP dump, we can get a much better understanding of what it was that traceroute was actually doing with the different flags, with the -T, -U, default, and -I flags sending the different packets. And we noticed that with -T, it sends traffic on port 80 by default, but we could change that port to anything we want. We noticed that it worked on ports marked as closed by Nmap. We noticed with the -I flag that it sends the ICMP echo request, waiting for an ICMP echo reply. With the -U flag, it sent a UDP packet on port 53, typically for DNS, and then on the default, it also sent a UDP packet, but it started those packets at a really high port number, up in the 33,000 range. So basically, this has been an overview of how the traceroute command works in Linux with the latest version of traceroute, version 2018 at the time of this video. And we took a look at all the different options that it has and how those different options can be used to get around firewalls to successfully do a traceroute. And we noted that the traceroute that comes with Windows is not going to be able to have near this much success because it only sends the ICMP packet, and you cannot tell it which port to hit, you cannot tell it which protocols to use, making it much more difficult to do this type of analysis from a Windows machine.